Greetings and salutations, magical chemists. Welcome to the glory that is thermochemistry, which deals with the energy changes that occur during chemical reactions. Now, you may remember that temperature is a measure of the average kinetic energy of the particles of a substance. And temperature is an intensive property. The amount of matter doesn't change the temperature. A tiny cup of water boils at 100 degrees, and so does a gallon of water. And the temperature, when measured in Kelvin, is directly proportional to the average kinetic energy. That means if you double the temperature in Kelvin, you've doubled the average kinetic energy. Of course, as you approach absolute zero, you'll be okay. Well, 0 Kelvin. The particles are approaching 0 kinetic energy. We like to represent the distribution of particles at different temperatures using a Maxwell-Boltzmann distribution because it's important to recognize that even though on average you can figure out the approximate kinetic energy, you're going to have different particles moving at different speeds. It's a range, it's a distribution. But what's important to recognize that if you are at a colder temperature, in this case colder is 300 Kelvin, on average the particles are moving more slowly than if you were at a higher temperature, in this case 1000 Kelvin. So it's interesting to note that even though higher temperature on average they're moving faster, there are still some particles at the high temperature that are moving more slowly than some of the particles at the colder temperature because it's an average. Yum, averages. Now, if you're in pre-cal, you will also be delighted to know, that we can use vectors to represent the different kinetic energies at different temperatures. All right, we've talked about temperature, so let's talk about thermal energy, because yes, those are different things. Now, thermal energy, which is heat energy, well, this is the internal energy of an object that's due to the kinetic energy of its particle, whereas the heat, or Q, that an object has, it's the amount of thermal energy it has that's capable of being transferred from one object to another. Now, heat, unlike temperature, is an extensive property. So it depends on how much stuff you have. Which is why, if you spill a thimbleful of burning water on yourself, it'll hurt, but it's not tragic. But if you spill a gallon of boiling water on yourself, they're the same temperature. But a larger amount of boiling water has a larger amount of heat it can transfer to your poor, poor, sad flesh. The moral of the story is, don't pour boiling water on yourself. Of course, heat will also always flow from something warmer, say the water, to something cooler, you. Again, don't pour boiling water on yourself. I didn't intend this to be a morality tale, but it's good to have life lessons. All right, now in thermochemistry, you may recall that the universe, the entire universe, is divided into two parts. We say two halves, but they're really not quite equal. The first one, the thing we care about, is called the system. This is the substance of interest, whatever you are studying, usually a chemical reaction for us. And then the surroundings are everything outside the system. All right, this will be important as we go along. Now let's remind you of one of the best equations of all. mcat. Why is it the best? Well, it's got a cat inside, of course. So mcat is the equation we use to calculate Q, aka the amount of heat being transferred. So if you recall, M is the mass of the substance measured in grams, C is the specific heat capacity, and delta T is T final minus T initial, the change in temperature. So let's look at the units involved here. Now, mass is measured in grams. Delta T, it can be in degrees Celsius or Kelvin. Shocking but true. We'll talk about that momentarily. Q, heat transferred, will be in joules. And so specific heat capacity, which we'll talk about momentarily, has these very unique units. It's called a derived unit because it's a combination of units. It's basically all the units you would need to cancel out so that Q is in joules. It is usually going to be in joules per gram degrees Celsius, or joules per gram Kelvin. Please note that if we're looking at the sign of delta T, N for Q, is talking about the object or the system you're studying. If heat has been added to the system or your object, it's positive signs. But if the system or your object is releasing heat, it's getting colder, that's what will give it a negative Q or a negative delta T, because your final temperature will be lower than your initial temperature, giving you a negative sign. Okay, let's go ahead and look at the glories of specific heat capacity, which we represent by C in mcat. Well, specific heat capacity is the amount of heat aka energy required to raise the temperature of exactly 1 gram of something by 1 Kelvin or 1 degree Celsius. That's where the units are coming from, literally the energy, which is joules divided by for 1 gram degree Celsius, or, Kelvin, whichever one you're looking at. Okay. Now, it is important to recognize that on average, metals have relatively low specific heat capacity. It doesn't take that much energy to heat up a metal. That's why metals get really hot in the sun really fast. Whereas water has a very high specific heat capacity. That's why if you leave an empty pot on the stove on heat, it'll get hot super fast. But, if you're waiting for water to boil, that takes forever. So for example, here are just a couple of different substances to compare. Notice, aluminum as a metal has a specific heat capacity of like 0.9. Liquid water, 4.184. And then glass, just another random solid, is 0.8. And some metals are a lot even lower than aluminum, so they can be like 0.3 or 0.2. But notice how water is 4? That's just, relatively speaking, I know 4, you're like, ooh, 4. But that's actually a really high specific heat capacity. Okay, let's go ahead and talk about why it doesn't matter if you're given degrees Celsius or Kelvin as long as your initial and final temperatures are in the same unit. Let's do that by trying an example. Okay, so we're going to calculate delta T. Now remember, delta T is T final minus T initial. And we are going to do this for a sample that started at 2 degrees Celsius and basically got heated up until 27 degrees Celsius. Well, so for our delta T is T final, which in this case, of course, was 27 degrees Celsius, minus T initial, which was our 2 degrees, which, yay, no calculator required, yum. That must have been a delta T, a change in temperature of 25 degrees Celsius. Okay, let's go ahead and do the same delta T, but we're going to do delta T this time for those temperatures in Kelvin. Well, 2 degrees Celsius, if we want to convert that to Kelvin, you are, of course, going to add 273. So we're going to have a starting temperature of 275 Kelvin and an ending temperature, well, if we add 27 to 273, we will get exactly 300 point, because, sig figs, Kelvin. So now let's calculate delta T again. So this time our final temperature was 300 Kelvin, and our initial temperature was 275. But hey, did you notice the change in temperature is the same number? Shocking, but true. It's because a degree of Celsius and 1 unit of Kelvin, it's the exact same temperature change. You've just shifted them upward to make sure that there's no negative temperatures. So this is why, if you're starting in degrees Celsius, you do not have to convert to Kelvin. You can, but why? It makes extra work. All right, and here is something shiny and new for AP. It turns out there's also a Q equals mcat. Just doesn't feel the same. In this case, N is the moles of a substance. Gasp! Because there is something known as a molar heat capacity. You'll know you're given a molar heat capacity because look at the units. The units you're dividing by moles. I covered up my smiley face. It felt wrong. So it's joules per mole degree Celsius. So just pay lots of attention for units. They are your friend. Okay, back to specific heat capacity. Just make sure you understand the idea that matter that has a low specific heat capacity is going to change temperature more if you're adding a specific amount of heat relative to something that has a high specific heat capacity. Let's consider some random made-up things to figure out why that is. Okay, let's look at substance A. Well, substance A has a specific heat capacity of 1 joule per gram degree Celsius, because 1 is a convenient number. And we're going to compare that to substance B. Substance B has a higher specific heat capacity. It takes 3 joules to heat up 1 gram of B, 1 degree Celsius. So let's say, hey, look at that. We have exactly 1 gram of each substance. How convenient. And we are going to add 3 joules of energy to each substance. Let's figure out what the final temperature is going to be. Okay, first, let's consider substance A. Well, remember we're adding 3 joules of heat, but the specific heat capacity is 1. Well, for every 1 joule of heat you have, when you add that to A, the temperature will go up by 1 degree. So when you added 1 joule of heat, the temperature went up by 1 degree Celsius. But we didn't just add 1 joule of heat, we added 3. And every time you added a joule of heat, well, the temperature went up another degree Celsius. So you can tell by adding the 3 joules of heat, I actually changed the temperature by 3 degrees. So the final temperature of substance A is going to be 28 degrees Celsius. Let's do the same thing for substance B. Now, substance B, of course, has a specific heat capacity of 3 joules per gram degree Celsius. So that means when I add all 3 joules, my 1 gram will only go up by 1 degree Celsius. But those are all the joules I had. So in this case, substance B only went up by 1 degree in total. So its final temperature from adding the exact same amount of heat is 26 degrees Celsius. So notice, the temperature that had a higher specific heat capacity changed temperature less because more energy was required before the temperature changed. Now, to be fair, let's say you consider an example where you're adding an unlimited supply of heat, which sounds impossible, but just think about like you put something in the sun, or honestly, you put something on the stove, turn on the burner, and just never turn it off. I don't recommend it, but it could happen. So if you're doing that, matter with a low specific heat is going to change temperature more quickly, whereas something with a higher specific heat, well, it's going to change temperature more slowly. All right, so now that you've had some lovely things to think about with specific heat capacity, let's try some practice questions. So, okay, notice they're giving you the specific heat capacities of solid aluminum, solid iron, and liquid mercury. Oh, and carbon. Whoops, there are 4 of them. So 2 questions for you. First question, when the same amount of heat is applied to 1 gram of these substances, which one will reach the highest temperature and why? And if you heat them all until they're all at the same temperature, which one required the most heat? All right, so I'm going to do my squiggly highlighting, which of course means you're totally going to try these practice problems. When you're ready to check your answer, go ahead and unpause the video. All right, let's see what you thought. If you said liquid mercury would reach the highest temperature, you win because it has the lowest specific heat capacity. That means that the same quantity of added heat will increase its temperature the most. Now, what about the one that's going to require the most heat? Well, in that case, if you said solid aluminum, again, you win. In that case, it's because solid aluminum has the highest specific heat capacity, so it requires more heat per unit of mass to raise its temperature. Now, to be fair, if this were a free response on the test, it wouldn't be enough to just say, oh, because it's got the lowest or the highest specific heat capacity. You'd have to fill in some details, like this. So it's always good to fully flesh out your answers. All right, we have one more practice problem at the bottom. So you've got a 45 cubic centimeter sample of copper metal and a 30 cubic centimeter sample of copper metal. Which one contains the most heat? Explain. And of course, when you're ready to check the answer, unpause the video. Well, if you said the 45 cubic centimeter sample contained the most heat, you would totally win. Remember, heat is extensive, and if you have more volume, you have more mass, so you have more heat. All right, hopefully you are getting a handle on specific heat capacity, so let's go ahead and try some mathy math. Yum, MCAT. So the first one is pretty straightforward because you want to know how much energy in joules does it take if you want to heat 15 milliliters of water from 273 Kelvin to 305 Kelvin. Now, one thing that is important to remember is that the density of water is the amazing 1 gram per milliliter. So if you have 15 milliliters of water, you have 15 grams. You don't even have to do any calculations for that. And then, of course, it gives you the specific heat capacity of water is 4.18 joules per gram degree Celsius. So go ahead and try this. Use the glories of MCAT, everyone's favorite equation, and see how much energy it would take. When you're ready to check your answer, unpause the video. So once you realized that you converted from milliliters to grams, the rest of this is just plug and play, because it says how much energy Well, you're solving for Q. So our mass was 15 grams. Remember, they gave you C, the specific heat capacity of water. Now notice that they gave us units of joules per gram degree Celsius, but these evil people gave us temperatures in Kelvin. That's not a problem. Joules per gram degree Celsius is the same unit as joules per gram Kelvin. So you don't have to do any conversions. You can just quickly make this a joule per gram Kelvin, because then when we plug in for delta T, which is T final minus T initial, you'll notice the units cancel delightfully, right? Grams will cancel, Kelvin will cancel, leaving only joules, which is perfect because that's what we were looking for. So when you multiply, you should get, well, you get something like 2008, right? But did you notice we only have 2 sig figs? So this is why we get to use scientific notation. Short and sweet. Let's try another one. Okay, there's a couple of sneaky things going on in this particular problem. If you're feeling brave, you should totally try it on your own. But if you pause momentarily, then I will go ahead and tell you about a couple of sneaky things. So, if you want to know the hints, first look at the units. Notice it's giving you Q, but Q needs to be in joules. So make sure before you plug into MCAT, you've converted from kilojoules to joules. And it's talking about heat being removed. So if heat is being removed, that means you have a negative Q value. So let's go ahead and plug into MCAT. Now the glorious thing is you don't actually have to show the conversion from kilojoules to joules. It's totally considered finally acceptable to just do that in your head. But make sure you are showing that it is a negative 596 joules because the energy was removed. It was lost by the system, in this case, the water. But after that, it's just plug and solve for a T final. Now there's all sorts of different ways to do the algebra. I thought it was easiest to divide away the 29.6 and the 4.18 to get TF minus 22.9 by itself. So notice how all the delicious units cancel out just the way you'd want them to. The joules cancels, the grams cancels, and you're left with 1 divided by 1 over Celsius, which is simply degrees Celsius. So when you plug in all those numbers, you get a negative 4.82. So now we can finally solve for the final temperature. Just realized I've been writing 22.4 and this is 22.9. Delicious problems with algebra. That will work much better. And so notice we get to keep 3 sig figs, but the problem here was that even though we get to keep 3 sig figs, that was going to 2 places after the decimal. Well, when I subtracted, 22.9 was only 1 place after the decimal, so I only get to keep 1 place after the decimal. Of course, ironically, that turns out to be 3 sig figs, so it works out. Notice the temperature, of course, is colder than when you started because you removed heat energy. Very logical. All right, let's try another one. Molar heat capacity. Notice, instead of being joules per gram degrees Celsius, we're given joules per mole degrees Celsius. Oh no, that's okay. We can still go ahead and use MCAT to solve this. Well, technically, NCAT. So go ahead and try this problem, and if you get stuck, unpause the video, and you can see how to keep going. Okay, so first, we have our 1.82 kilojoules, which means, of course, for Q, we've got 1,820 joules. You have to make sure when you are doing Q that you are in joules. Now, N, of course, is the number of moles, but we don't know that. Well, we're trying to find the mass. Before we can find the mass, we got to find moles first. So we don't know this value, but we can plug in the things that we do know. We know the molar heat capacity. And you may be wondering, wait a sec, I don't have an initial and final temperature. That's okay. They actually just gave you the temperature changed by 52 degrees Celsius. So 52 degrees Celsius is your delta T value. No subtraction required. So now, solving for N is delightful algebra. So we can cancel out our units. Noticing, of course, that this means we solve for moles, but they want us to find mass. Well, if you know how many moles of mercury you have, it's really easy to find mass. That's what molar mass is made for. Well, straight from the periodic table, the molar mass of mercury was 200.59 grams in a mole. Now, since we only get to keep 2 sig figs, this means my sample of mercury must have been just about 250 grams of mercury. Ta-da! All right, one more to go. Guess what? This is going to be your practice problem, all yours. Aren't you totally excited? So you're solving for the specific heat of copper, given this information. I will even pretend to be a nice human and I will give you the right answer so you can check your work when you get there. But, of course, you have to have the work to back it up to get the stamp sheet grade. All right, I have given you the correct number. It is your job to solve this problem all on your very, very own, and I didn't even give you the units because I am a terrible person. I know. All right, hopefully you've had lots of fun playing with thermochemistry, and I will see you for the next video about calorimetry. Even more heat. We're going to be on fire. It'll be awesome.